Dear students, I welcome you all to this problem solution series in digital electronics. I am solving the problems from the book Digital Design by Maurice Mano and Michael Ciletti. So in this video, I am solving the problem number 6.9 from the chapter number 6. So the problem is two ways to implement a serial adder A plus B are presented in section 2. That means in section 2, we will find a serial adder that will add the two numbers A and B. It is necessary to modify the circuit to convert them to a serial subtractor. That means in section 2 we are given with a serial adder that will add the two bits A plus B. And here we have to modify those circuits to make it a subtractor that will subtract the number B from A. So here we have two parts in this question. In the first part, using the circuit of figure 6.5, this figure is from inside of the chapter. In the previous problem we have seen this figure 6.5 shows the changes needed to perform A plus 2's complement of B, that is A plus 2's complement of B. So subtraction can be done by adding the 2's complement of the subtrahend. And the second part of the problem is using circuit of figure 6.6 show the changes needed by modifying table 6.2 from an adder to subtractor circuit. That means this figure we have to convert from an adder into a subtractor. First of all, let us start with this first problem, part A. So first of all, let us understand what is a subtractor. Suppose 1001 and we have to subtract a number, suppose 0010. We can do the subtraction by adding the 2's complement of the subtrahend with the minus n. So if we find out the 1's complement of this number, that is the bits will be inverted, that is 0010, it will be 1101. That means 0 will become 1 and 1 will become 0. Okay, so this is the 1's complement, and if we add 1 with the 1's complement, we will get the 2's complement. So it will be 1110. Now if we add this 2's complement with the minus n, we will get 1001. We will get 0 plus 1, it will be 1, 1, 1, 0 and 1. So this 1 will be discarded. Okay, so this is the answer. So if we add the 2's complement of the subtrahend with the minus n, we will get the subtraction of the two number. So this is the figure 6.5 from the chapter. So here we can see that we have two resistors A and B. This is resistor A and this is resistor B. So this is a serial adder circuit. Now we have to make this a serial subtractor circuit. So what we have to do, we have to find out the 2's complement of the number B, that is the 2's complement of the subtrahend, and add the 2's complement with the minus n, that is A. First put an inverter here so that it becomes 1's complement, and if we make this carry in is equal to 1, we will get the 2's complement. We are getting directly the minus n here, and we are getting a 1's complement here, and if we add 1, we will get the 2's complement. That is, we are adding the minus n to the 2's complement of this subtrahend number. So here we will get the difference. So we can write here in figure 6.5, complement the serial output of resistor B and set the initial carry value equal to 1. Now let us redraw this circuit of figure 6.5. So here we'll have, suppose this is resistor A. So shift resistor A. So here we'll have serial out. Okay, and here we'll have the serial in. Here we have shift control. Okay, here we'll have the clock, and here we'll have the shift resistor B, shift resistor B. Here we'll have suppose serial out. Okay, similar to this one. Here we'll have the serial in. Here also it is serial in. So we will have here the load. So this is load. So shift control also we have to apply here. Okay, and clock also we have to apply here, and bring this to downside and use a AND gate, and the output of this AND gate will work as a clock to this D flip-flop. So here we have D input, here we'll have the clock input. This clock will be connected to this AND output and get output. So here we'll have a clear, here we'll have a full adder. Okay, it will have two number that will be added, and here we'll have a carry input. So carry input is the output of this D flip-flop. Here we have Q output. Okay, so this is D flip-flop. This output is the carry output here. So here we'll have this carry out, because here we have to use a full adder only. Okay, and the sum output will apply to this serial input, and here also it will be the same as the previous one. Okay, but for this second input, that is y, for this y input of this full adder, we have to find out the 2's complement of this number. So first of all, here we will set a provision to set 1, okay, at this D flip-flop. So initially we will make this 1, this carry input will be 1, okay, and we have to add the complement. That means what we have to do, we have to apply a inverter here. Okay, so this is a NOT gate, and we will apply this to this Y input. So here we have the 1's complement of this number B, okay, and this will be added to this carry in, that is initially is 1, that is it will become the 2's complement, and this 2 complement will be added to this minus n x. So here we have a feedback from here to this serial input. So this is the modified circuit of figure 6.5. So here we'll get the difference here now, because we have added the 2's complement now. So here we get the difference. Now let us go to our part 2. In the second part of the problem, we have to use the figure 6.6, okay, and show the changes needed by modifying the table 6.2 from an adder to subtractor circuit. So we have to modify the table number 6.2. So table 6.2 is this one. So from book, this is the table number 6.2. So this is the state table of serial adder. So we have to modify this circuit, and we have to find out the JQ and KQ values for this figure. So this is the figure 6.6. We have to modify this figure by modifying the table 6.2. Okay, so we have to modify this JQ and KQ inputs, okay, of this circuit, and we have to make it as a serial subtractor. So here we have present state, then we'll have inputs. Present state is suppose Q of t, inputs are x and y, okay, and the next state is Q of t plus 1, okay. The output now will be the difference, okay, because so this was a serial adder table, so this output was the sum. Now here we'll get the output will be the difference, okay, so we'll denote it with D, okay, the output will be D, and we have to find out the flip-flop inputs, respective flip-flop inputs. So the flip-flop inputs will be this J and K, okay, so here we'll write JQ and KQ. So we have to make this table first. So for the adder circuit as shown in figure 6.6, this Q of t is nothing but the carry input, okay, and this next state of Q of t plus 1 is the carry output. But here we are going to design a subtractor circuit, so this will be output will be the difference, and the next state will be the borrow out, and this is the suppose borrow in. Now let us write down the this input combination. Suppose here we have 0 0 0 0 0 1 0 1 0 0 1 1, okay, 1 0 0 1 0 1 1 1 0 1 1 1. So now we have to find out the next state of q of t plus 1. So for finding out this output d, that is the difference, and this borrow out, so we have to consider x minus y, and then we have to subtract the borrow in. So here we'll have 0 minus 0, so difference is 0 and borrow is also 0. Next we have 0 minus 1, input borrow is 0, so 0 minus 1 minus 0, so it will have output but difference is 1 and borrow is 1. 0 minus 1, we have to take 1 borrow, and after taking 1 borrow it will be 1 0, and from 1 0 if we subtract 1 we'll get 1. Next we have 1 minus 0, so 1 minus 0, the difference will be 1 and the borrow is 0. Next we have 1 minus 1, so the difference is 0 and borrow is also 0 because we do not have a borrow in here. If we see here 0 minus 0, so the difference will be 0 and the borrow is also 0, but here we have a borrow in, so we have to subtract this number also. So 0 minus 0 minus 1, so we'll have here difference is 1 and borrow is also 1. That means we have to take 1 borrow to subtract 1 from 0, so we'll have here difference is 1 and borrow is also 1. Next we have 0 minus 1, but we'll have difference is 1 and borrow is 1. Okay, but if we have borrow also 1, so what we'll have, so difference will be 0 and borrow will remain 1. So the operation is 0 minus 1 minus 1. So 0 minus 1 will have difference is 1 and borrow is also 1. Okay, next we have to subtract this one also, so the difference will be 0 and borrow will be 1. Next we have 1 minus 0, so it will be 1 and 1 minus 1, it will be 0. So 0 and 0, difference is 0 and borrow is 0. Next we have 1 minus 1, so the difference is 0, borrow is 0. From 0 we have to subtract again 1, so we'll have here difference is 1 and borrow is also 1. So we have got the next state values and the difference output values. Okay, so using excitation table of JK flip-flop, we have to find out the J and K values. So we have to use this excitation table of JK flip-flop. So here we'll use this excitation table Q of T plus 1. So J and K. So for 0 0, that is present state 0, next state 0 will have 0, don't care. For 0 1 it will be 1, don't care. Next for 1 0 we'll have don't care 1, and we have already seen this. Okay, so 1 1 will have don't care and 0. So we have to use this excitation table for finding out the values of JQ and KQ. So for here we have 0 0, so here we'll have 0 and don't care. So here we have 0 1, okay, so we'll have 1, don't care. Next we have 0 0, so 0, don't care. So 0 0 again, 0 and don't care. Next we have this 1 1, so we'll have don't care 0. Next we have 1 1, so don't care and 0. Next we have 1 0, so it will be don't care 1. And next we have 1 1, so don't care 0. So these are the respective JQ and KQ inputs. So for designing the circuit, first of all we have to find out the expression for D, J and K, that is difference J input, K input. Okay, so first of all let us find out the expression for suppose D. So K map for D. So here we'll have three variable map. Okay, Q, X, Y. 0 0 0 1 1 1 1 0. So 0 1. Now we have to fill up the values of D here. So 0 1 1 0 1 0 0 1. 0 1 1 0 1 0 0 1. So we have to take like this. So this will be the combinations. Okay, so here we'll have D is equal to, suppose from this term we will get it is X bar Y bar Q, X bar Y bar Q, plus for this term we'll have it is X bar Y Q bar, X bar Y Q bar, plus from this term we'll get X Y Q, X Y Q, and for this term we'll get it is X Y bar Q bar. x y bar q bar. Okay, if we take q common from this first and the third term, we'll get x bar y bar plus xy whole into q, plus if we take q bar common from the second and the fourth term, we'll get x bar y plus xy bar whole into q bar. Okay, so here we'll get this is x nor operation, x nor y whole into q, plus this is XOR operation, so x XOR y q complement. Next, this XNOR is the opposite of XOR. Okay, so we can write it as x XOR y whole complement q plus x XOR y q complement. So here we'll get this is the a bar b plus a b bar form. So we can write x XOR y XOR q. So this is the expression for D. Now we have to find out the expression for JQ. So K map for JQ. So here we'll have a three variable map 0 0 0 1 1 1 1 0 0 1 q x y. Now we have to put the values of JQ here. So JQ is 0 1 0 0. Don't care, don't care, don't care, don't care. So here we'll have 0 1 0 0. Don't care, don't care, don't care, don't care condition. So this will be the one term. So from this combination we'll get JQ is equal to, this is x bar y, x bar y. Now we will find out the K map for KQ. So here also we'll have a three variable map 0 0 0 1 1 1 1 0 0 1 q x y. Okay, now we have to fill this K map with the values of KQ. So KQ value is don't care, don't care, don't care 0 0 1 0. Don't care, don't care, don't care, don't care 0 0 1 0. So we can combine like this. Therefore KQ is equal to x y bar, x y bar. So we have got the expression for this difference, this JQ and KQ. So now we can modify the circuit of figure 6.6. So this is figure 6.6. So now we have to modify this inputs JQ and KQ and this D. Here we will have the difference. So let me draw the modified circuit. So here we'll have shift resistor A. So this is shift resistor A. So here we'll have serial output. Here we'll have serial input SI and SO. So this output is nothing but X. Similarly, here we'll have the shift resistor B. Shift resistor B. Here we'll have the serial output. This is Y. Okay. So here we'll have the serial input. So here we have to apply the shift control. Shift control. Next we have to apply here a clock CLK. This is the clock pulse. And this shift control also we have to apply here. So we have to give here the serial input. So here we'll have serial input, serial input. Okay, at this shift resistor B, that is we have to apply here the subtraction. So here we have to apply the minus n. So here we'll have a JK flip-flop. So we have to take a line from here. Take a line from here. Use a AND gate. That means whenever we have both this shift control and the clock is 1, this flip-flop will be activated. That is, this output of this flip-flop is connected to the clock input of this JK flip-flop. Here we have J input, here we'll have K input. So this is J input, this is K input. So we have got this X and Y. Here we have J and K. So the expression for J is X bar Y. So here we have suppose X bar Y at this output. Here we have to apply X bar. So you say inverter here, so here we'll get x bar. Okay, and we have to directly apply this y here. Okay, so here we'll get x bar y. So this x bar y will be connected to the j input. Okay, so connect these lines to this j input of this jk flip flop. Here we'll have the normal output q. Okay, so for kq we have x y bar. So take a line from x and you say not get here to complement this y. Okay, you say and get, here we'll get x y bar. So connect this line to this k input, because we have got the expression for kq is x y bar. So here we have got x y bar. Okay, now we have to find out the d difference, that is the XOR operation between x, y and q. So here we have this q. So use here a XOR gate, and this output will be the difference. So this difference is feedback to this serial input. So the inputs are x, y and q. So take a line from this x and apply here. So take a line from y and apply it here. And the third input is q. So take a line from q and apply it here. So here we'll have the difference. So this is the modified design of the circuit for the subtraction of a minus b. A value will be stored in this shift register A, okay, and b value will be stored in this shift register B, and here we will get this difference. So this is the solution of the part B. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Thank you.